My dear students, welcome back. So in the continuation to my previous class, so in the previous class we had done about the damped oscillations, and we had written down the differential equation for the damped oscillations, and then we had solved that equation to find out the equation for the displacement. So from that equation of the displacement, we observe that the amplitude does not remain constant for a long displacement. So that is, it is continuously going to oscillate. Its amplitude is going to decrease, right, slowly, and that type of the oscillation is called damped oscillation. Now today we are going to look into what are the different types of the damped oscillation. So damped oscillation is not only one type. We have the different type of the damped oscillations, and as I had promised you in the previous class that we have some critical and very good applications, even the engineering applications of the damped oscillations. So some of the applications will be looking into, right? And then as you graduate, you go to the higher semesters, you'll be looking into the different electronic applications of your damped oscillation. So let us see what is the damped oscillation that we have already done, and how we can divide the damped oscillations into the different parts. So now this goes to the types of damped oscillations. So depending upon the relation between the damping coefficient. So if you remember your equation, the differential equation that we had done. So there in that differential equation we had taken two constants. One was your gamma. Gamma was equal to your B by M, where B was your resistive medium, the coefficient of the resistive medium, and M was the mass of the oscillating object, and omega naught was the natural frequency of the object. So depending upon the relation between the constant gamma and natural frequency of omega naught, there are the following three types of the damping involved, and we know that the differential equation for the damping is given by d square x upon dt square plus k by m plus b by m dx upon dt is equal to 0. So this differential equation we had derived in the previous class, and then we had solved this differential equation for the value of x. So what will be the value of the x? That is the displacement. That here displacement does mean the amplitude. So how does the displacement, that is amplitude, is going to vary? That mathematical form we have already derived. So what I have told you there, k by m is called your natural frequency, and that we are representing by the omega naught, and b by m is called your another constant, where b is your constant of the damping medium, and m we had called as the mass, which was oscillating, and b by m we had called as the damping coefficient, which we had represented by 2 gamma, right? So b by m we had taken as equal to 2 gamma. So depending upon the relation between omega naught, so what we are saying, this is your omega k by m, your omega naught square, and b by m equal to 2 gamma. So depending upon the relation between omega naught, that is your natural frequency, and gamma, that is your for your damping medium, right? Because mass is always constant, right? The differential equation that we had got was equal to x equal to a e power minus gamma t sine omega t, where gamma is equal to minus b by 2m, that you are aware of this, and sine omega t is going to give you the sinusoidal wave, right? And phi is the initial phase that has got established, and x is given as your amplitude. So this is how the amplitude of the damped oscillations is going to vary. Now how we can classify the different type of the damped oscillation? We can classify this different type of the damped oscillation depending upon the value of the natural frequency omega naught and the gamma. Now you can say there is no omega naught here, but what is this? This value of your omega is equal to gamma under root gamma square minus omega naught square, that with which we had replaced this by the value of the omega, that you can see in the previous class lectures. So now we have the following three types of the damped oscillations. And what are these damped oscillations? First we are calling the light damping, where the gamma is less than your natural frequency omega naught. Then second is called your heavy damp, or this is also called your over damping, where gamma is greater than omega naught. Omega naught again is your natural frequency, and gamma is your damping medium, and this omega is equal to your gamma naught. So these are your three type of the damped oscillations. These are not different types of the oscillation. These are the three types of the damped oscillation depending upon the value of your damping medium, that is your gamma. Gamma is nothing b by 2m, and your natural frequency, the natural frequency with which the spring was oscillating. All right. So now you see this diagram. In this diagram here you can see the again we have taken the three types of the oscillations. First we have taken the light damping. So light damping has been shown with this red curve that you are able to see here. So this is representing you the damped oscillation. So what you are finding over here, that is a lightly damped. This is your lightly damped. And what you are finding here, that the amplitude is slowly decreasing as we are passing with the time. Then second is called your heavy damping. So this is your heavy damping. This is the graph for your heavy damping. So what you are finding out, that it is not oscillating at all. Its amplitude is decreasing with the time, and after a very long time its amplitude is going to become zero. That is, you can just imagine that you have a stretch spring, right? So this is your you have got a particular amplitude. That amplitude we are calling as A naught, and from there it is taking very long time in coming back to its original position. If that type of the oscillations you are able to provide, that will be called as over damped oscillations. And the third one is your critically damped. So here this is your critically damped. In this case also you can see it is not oscillating at all. Here also this is not oscillating at all. Here you have only one amplitude, and this amplitude has become zero. But now you see what is the difference between the over damped and lightly damped. In case of critically damped, in case of the over damped, it is taking very long time to become its amplitude zero. Now here even the amplitude has not come zero, so it will take further time because this axis is with the time. So it is going to take very long time when its amplitude is going to be zero. But in case of the critically damped, as you can see, in case of the critically damped, this amplitude is becoming zero at a quickest interval of the time, and then it stops. It is not going to further down, right? So it is not going to repeat its amplitude, its motion, and this type of the oscillation will be called as your critically damped oscillations. So what we are finding, light damping involves oscillatory motion. So as you can see this red one, so this red one is oscillating, of course with the reduced amplitude is slowly decreasing. So here only you are getting the oscillatory motion, whereas in both the case of the over damped and critically damped, there is no oscillations at all. Just they will come to its initial position, and there only it is going to stop. So now all these three cases we are going to look into in more detail. So let us look into the all the types one by one. So now let us see about the light damping. So let us consider a mass m immersed in a fluid. We assume that the viscosity of the fluid is low, like a thin oil or just even air. So what you can consider over here, that here you have a simple pendulum, and simple pendulum is oscillating in air medium. So as it is oscillating in the air medium, its amplitude is going to decrease. So let us suppose initially its amplitude is this much, then after certain time its amplitude will become this much, right? So with the time this amplitude is going to decrease, and this type of the motion is called your lightly damped oscillations, right? The parameter gamma and omega. What is the gamma? Gamma we know is about your medium in which it is oscillating, right? And omega naught, here we can say omega naught. Omega naught is nothing, is your natural frequency. So these are the property of the oscillators. Naturally, the one is your natural frequency, other is the medium, while x naught, which is your amplitude, and the phase phi are determined by the initial conditions. So with this initial condition, how much it is going to make the maximum amplitude, and what is the phase, all these are your initial condition of the oscillations. It is nothing related with your oscillator. Next we are saying, if gamma is equal to 0, so if gamma is going to be 0, it does mean we don't have resistive medium, and if you don't have any resistive medium, it become your free oscillations. So it will become your simple harmonic oscillator if the gamma value is coming to be equal to 0. So naturally it will not be called as the light damping. It will not be the damped oscillations. It will be free oscillations, right? So now this is your example in which we have already derived this equation, a e to power minus b by 2m. This is what we call gamma minus b by 2m. We had to represent by gamma into t, and then we had sine omega t plus phi. Let's forget right now sine omega t plus phi. So what I am saying, this is nothing. This is your amplitude. This is your amplitude. So how this amplitude is going to decrease, because this is showing it is exponentially, it is going to decrease, minus b by 2m. B by 2m is nothing, say gamma into t. So exponentially it is going to decrease. So this type of the oscillations we'll see only when the value we have the medium where we have very small value of the resistive force. So the present graph shows the weak damping, therefore gamma is very less than omega naught, right? Because it's a very small value, so value of the gamma is very small, right? For the simplicity, we have set the phase is equal to 0, and we see that the successive maxima decreases by the same fractional amount. This is nothing, this is a logarithmic decrement. So logarithmically what we are finding over here, as you can see, the amplitude is decreasing with the time, and this type of the oscillation is called your light damping oscillations, right? So this was your first type of the oscillations. Let's move to the next one. All right, so further we are going to continue in this only. Mathematically the equation that we have derived is x equal to, x is your amplitude, a e to power minus gamma t, right? So a e to power gamma t is, this is how the amplitude is going to vary. So this is your amplitude term, and this is your wave, sine wave. So how the amplitude is going to vary, how the x is going to vary, a e to power minus gamma t. Normally you have only a. In the free oscillations, you have a sine omega t plus phi. But what here you are finding a e to power minus gamma t sine omega t minus phi. So here minus gamma t is showing that its amplitude is exponentially decreasing, right? The above equation is a simple harmonic equation with the amplitude a e to power minus gamma t, and of course its time period is equal to nothing, 2 pi by omega, and omega is how much? Omega naught square minus gamma square. We have already seen this. So this omega that we have got, this value of the omega that we have got is, omega is nothing, omega naught square minus gamma square, where omega naught is your natural frequency and gamma is your damping coefficient, right? So this is your mathematical representation of the time period. So now what we are finding here, if you see this, let us suppose this I am saying as the equation number A. So from this equation number A, what we are finding is amplitude is going to decrease and is a sinusoidal wave. Of course it is propagating with a constant phase. For the simplicity we have taken phase equal to 0. So what I am finding, that it is making a sine wave, but its amplitude is progressively decreasing with the time t. So this is your time t, and this is the amplitude that has been represented, +1, -1, and as we are moving with the time, let us suppose we have come up to the 55 seconds, and by the time its amplitude has come down to 0, right? Thus the amplitude of simple harmonic motion is continuously decreasing due to its first term. Naturally this is the first term about which we are discussing. So because of the first term does mean this, because of this term a e to power minus gamma t, because of this it is continuously decreasing, and that is known as the damping factor. So a e to power minus gamma t will call as your damping factor. The second term is known is a sine wave, which will vary between -1 to +1 naturally. So leading to the variation of the amplitude from a e to power minus gamma t to minus a e to power minus gamma t. So this is your value of a e to power gamma t, and to the a e to power minus gamma t, between these two limit it is going to vary. The decay is dependent on the decay coefficient. In absence of the damping coefficient gamma, the time period of course will be given as t equal to 2 pi by omega naught, where omega naught is your natural frequency. So now you see the difference. Here in case of the damped oscillations, that is lightly damped oscillations, here we are saying it is your 2 pi upon omega naught square minus gamma square. Omega naught square minus gamma square, right? This is your time period. But in case of your free oscillations, it is equal to 2 pi upon omega naught, and omega naught is equal to under root k by m. So just you are going to substitute the value of omega naught k by m. You are going to rearrange and you are going to find out what will be the time period. So this will be called your light damping. Right now, let us come to the next one, and this is your overdamped. So what is happening? What is the case of the overdamp? I had already told you that in my first slide, that in this value, the value of the gamma is going to be very large, very large than your natural frequency. That is, a damping medium is very thick medium, right? Than your natural frequency. So you can give an example. First, let us read what is written over here. A heavy damping occurs when a degree of the damping is sufficiently large that the system returns sluggishly to its equilibrium position without making any oscillation at all. Thus, this corresponds to a mass being immersed in a fluid of large viscosity like syrup. So now all of you must have seen the coal tar. So let us suppose here here you have a coal tar, and this is a container. This container is filled up with the coal tar, and here we have the same spring system, right? The same spring system. So this is your spring system, and this is the mass is immersed inside your coal tar, and then this is the under the mass. This is the amplitude you have given. Now it has to return back. Let us suppose this is your initial position. This is your initial position. So now it has to return back to its initial position. Now you can imagine how much time it will take to come back to the initial position, because the coal tar is so much thick that it will not allow the spring to come back to its original position. So we can say practically it is going to take very long time to come back to its original position, and that type of the oscillation will be called overdamp. Once it has come to the original position, it is not going to come back again to the other position from where it has returned back. It is not going to come back to that position, and that type of the oscillations will be called as overdamped oscillations. Right. So here this is the, again I have represented you with the diagram. So in case of the overdamp, so let us suppose this is your initial amplitude. This is your initial amplitude, and the initial amplitude I am saying it will be x by m. So this I will explain you how I have taken x by m, maybe in the case of the force oscillations, right? Forget it. Let us suppose this is your initial amplitude, this is your a, and this initial amplitude a is going to become infinitely small or even equal to 0 in a very long interval of the time. So this is the time it has taken, right, in making its amplitude 0, that is in coming to the 0 position, right? So this type of the oscillations will be called as your heavily damped oscillations, right, where it is going to take a very long time to return back to its 0 displacement position, right? So this was your initial with a displacement position. Once displacement you have given, and then to come back to the original position, it is going to take very long time, right? And that type of the oscillation will be called heavily damped oscillation. So let us see a bit mathematically. For over damped condition, naturally your gamma should be equal to should be greater than and very greater than omega naught. Right now, if you see this equation, this is the equation that we had derived in case of your the damped oscillations. X equal to c exponential minus gamma plus under root gamma square minus omega naught square, and this is the value that we had called as omega naught. This is the value that we had called as omega naught plus d exponential minus gamma under root gamma square minus omega naught square into t. So here c exponential minus gamma into t, c exponential minus gamma into t, because t is common over here, and here again d exponential gamma into t. So here both the terms are negative. Both the terms are negative, so both the amplitude are negative, and therefore what we mean that both the displacement terms are exponentially dying down to zero without performing any oscillations, right? And therefore once it will come back to the zeroth position, it is never going to return back, and this type of the oscillations will be called as overdamped oscillations, right? So now we are moving to the, and this is your critically damped oscillations, and where we are going to deal with some of the engineering applications. Let us see carefully. An interesting situation occurs when gamma naught is equal to omega naught. That is the natural frequency omega naught and the damping medium, the coefficient of the damping medium, both of them are equal, right? In the case of the critically damping, mass return to its equilibrium position in the shortest possible time without oscillating. So now you find out the difference between the heavy damping and critically damping. In case of the critically damping, it is going to return back to its original position in the quickest interval of the time, right? Very fastly it is going to return back, right, to its original position, that is the zero displacement, but after that it is not going to return back, right? So the critical damp has many important practical applications, and I'm going to take up one by one. First, let us see the case of the door closer, where all of you are using in your home, right, or your offices, the door closer. What do you have? A spring may be fitted to a door to return to its closed position after it has been opened. So when you open the door, right, if the door closer is fitted, slowly the door get closed, right? In practice, however, the critical damping is applied to the spring mechanism so that the door returns quickly to the closed position without oscillating. How it works? Let us try to understand with this diagram. So this is how in your house you have the door fitting. So this is your this is your door closer. So this position that you are seeing over here, this is nothing. This is your door closer. So in this door closer, what you are finding, that here you have a spring. This is your spring. So here you will have the spring. This one is your spring, and here this is one of the chamber, and this chamber is filled up with some oil, right? So piston or piston, this is your piston rod will go immerse inside the oil, right? So this oil will be nothing. This will be a damping medium. This will be your damping medium, which is going to control the movement of the spring. So that spring is going to be damped with the help of this damping medium, and therefore when you are going to open this door, let us suppose this door has been opened. When you are going to open this door, so door will be quickly come. So here this will bring back to its normal position. It will come over here, but then this is going to be damped, right, in such a way that once it has come over here, it is not going to return back. So its damping coefficient will be in such a way, right, it is such a way calibrated depending upon the normal weight of the door, so that after it has been set, it is not going to return back. So this is how the value of the damping coefficient of the oil is being calibrated or calculated, and that type of the oil is being filled so that the piston will come to the one position, and then piston is not able to push the spring, and the door will not open again. And this is the one of the application of in the door closer. Let us see another one application, that is your analog electrical meter. So you are using the ammeter, voltmeter. I'm not talking about the digital, the analog one, in which you have the indicator which moves, right? In that indicator, if you don't have the damping, then indicator will vibrate. So you will not be able to take the accurate reading. So let us see what I have written here. The critical damping is applied to the analog meter for the electrical measurements. This ensures that the needle of the meter moves smoothly to its final position without oscillating or overshooting, so that the rapid reading can be taken. Let us see, try to understand with the diagram. So here, if you open your ammeter or voltmeter in your lab, you can do that sometime. You'll find your indicator is attached with the spring, and inside this spring is also closed inside a small vessel, and here some damping medium is applied in this spring, right? So this spring is going to be damped. So while this is going to move, the movement of this indicator is going to be controlled by this spring naturally, and of course with the current or voltage that you are going to provide. then accordingly this indicator is going to move on this. So let us suppose the indicator has moved to this position here, but at this position it will not vibrate, it will not go like this, it will go at one particular point and it will become static. So here the spring is calibrated in such a way that whatever the value it has been shown, it will go at that value and it will stop there. It is not going to vibrate. But if you are not going to put this spring there, then it will start vibrating. And a spring also, it should not be it should be critically damped, then only it will not vibrate. Otherwise, if you, let us suppose if you are putting the over damped type of the spring or the under damped type of the spring, it is going to oscillate. So what you have to do, you have to critically, you have to take the medium in which medium it is going to oscillate, right? And for that medium, it should not vibrate, right? So the value of the medium, so naturally say air, right? So in the air medium, what should be the value of the damping coefficient of the spring, so that both of these should match? That is, the spring constant and the resistive force of the air, both of these should match, that it will not vibrate at any point and it will give you the exact reading. And this is how in this voltmeter or similarly in case of the ammeter, you take the exact reading. So this is one of the applications of your critically damped. Now I am coming to the little more exciting type of your example on your critically damped oscillations, and this shock absorber in your car. So while you are moving in your car, right, so here you have the car, and in this car what you find that at the wheel there is a shock absorber. So this type of the shock absorber is there. What is the function of this shock absorber? So this is your body suspensions, right? So on this body suspension, body or your car frame, you can say, this is your suspension spring, and between the suspension spring and the car, this is a shock absorber is attached. This is your shock absorber that we are attaching between them. Now what is the role of this shock absorber? All of you are knowing. So one modern day application of the damped oscillation is the car suspension system. What is its role? The suspension system of a car makes use of the damping to make the rides less bumpy and more comfortable by contracting and hence reducing the vibration of the car when it is on the road. So now what happens? Let us suppose the car is moving and suddenly you have come across a speed breaker. Car will jump over the speed breaker, but if you don't have the shock absorber, the car will start oscillating up and down, up and down, up and down, and it will not give you the comfortable ride. So what you should have, that the car should not oscillate once it has come down, right? Naturally, if it is going to vibrate, going to jump the speed breaker, the body is going to come down, and then slowly it should go up, and then it should not come down, that is, it should not vibrate, and then you will have this smooth ride. For that, we are putting the shock absorber, and how it is working, this is what I am going to deal with. So picture shows the shock absorber at the bottom. So this is the shock absorber that I have shown you here, the red. This shock absorber that I have shown you the red, same shock absorber has been shown over here. The piston, which is in a reservoir of the oil, moves up and down in relation to the vibration of the car. Now you try to understand this. Now what is our aim? The car should not do up and down, up and down, up and down. It should not vibrate, right? Once it has crossed the bumpy road or the speed breaker, it should become constant. Immediately it should come to the normal position. For this, you have put the shock absorber right on the suspension spring. How it works? Now here in this shock absorber, as you can see, it is filled up with the oil. So this is filled up with the oil, right? And this is your piston. The piston is free to go up and down, to up and down, right? To absorb the oscillations, right, or the shocks. Now in the frame of this, you have the holes. As you can see, you have the holes. So as it is moving, the oil is going to pass through this like this, right? So it is going to pass through this. So because of these holes, the piston is able to move inside this, right? Naturally, if you don't have the hole, then it will not be able to move inside, because it's a closed, it's a filled up with the oil, and therefore it will not be able to move up. So what is happening, it is slowly as the car has given you the bump, this piston will slowly move up, right? It will go to a certain position, and then it will not return back. The piston will not return back, or even if it is going to return back, very small value it is going to return back, and it will it will stop this. Now how it works? So not naturally the oscillations which has suffered in the wheel, oscillations which have suffered in the wheel has been transported into the pistons in this piston, and in the turn the piston has started pressing the oil, and the oil has been calibrated in such a way that it will allow the piston to move to up to a certain distance, and after that it will stop it. The piston will not move beyond that position, and the car will come to normal position. So this is, it does mean the piston has been critically damped, right? It will just come to the original position, and then it is not going to come back. So this type of the things, if you are going to do, the car is not going to vibrate. So this is what I'm telling you. The holes in the piston head permit the piston to pass through the oil. So through the oil, the piston is going to move. The viscous forces that arise due to the movement cause the damping. So naturally, this is the oil. So oil will have a particular value of the viscous force, and that viscous force is against the motion, and that is going to stop the further movement of the piston inside the fluid. Okay, as the wheels on the car move up and down, the suspension systems provide a contracting force opposite to the direction of the motion of the car's wheel, right? So this is what I have discussed. The shock absorber are able to do so as they provide velocity dependent damping force. So this damping force is velocity dependent, right? So more is the velocity, more will be the damping, less is the velocity, less will be the damping. So it is a velocity dependent, right? And all type of the velocity it is able to absorb it. The direction of the force always oppose the car's up and down motion. This is what I explained you. The direction of the force always opposes the car's up and down motion, so that when the car goes over the bump, it helps to contract the vertical motion of the wheel and not further contribute to it. The damping force of the suspension causes the amplitude of the vibration of the wheel to decrease until it reaches to zero. So the vibration is ultimately reaching to zero. In the optimal situation, the system should have enough damping such that it only oscillates or bounces once or twice for each bump in the road. It should not be beyond this, right? So the fluid that we are providing, the oil that we are providing, it will have the such type of the damping coefficient that it will not allow to do up and down more than once, twice, right? So that was your the shock absorber in the car, which is possible with the critical damping. Now this is your graphical representation of all the three types of the damped oscillations. So firstly we have the underdamped, the A, as you can see over here, this is your underdamped, and in this case only you have the oscillations. So as you can see over here, it is oscillations, and with the oscillations you are getting with the time its amplitude is decreasing. Secondly, we have the critically damping, as we have seen. So the red one is your critically damping. So in case of the critically damping, it is coming to the zero position or nil point in the quickest possible time. So this is your critically damped. And in case of the over damped, right, it will take very long time to come at the zero position, that is the zero displacement. It will, or the initial position, you can say. It will take very long time to come to the zero displacement position, right? And of course it is not going to make any oscillation, it is not going to come back. So both the critically damped and overdamp, they are not going to come back to its it is not going to make the oscillations. It will only be coming back to the original position, and then it is not going to further oscillate. But in case of the light damping, it is going to oscillate. So what I have written here, for critically damped and overdamped oscillators, there is no periodic motion, right? So periodic motion is not there in both the cases, that is the critical damp and overdamp. And angular frequency omega has a different meaning over there. So in this way, in complete sense, we have finished your damping oscillations. Now, as we have finished all the type of the damping oscillations, right? So now in the next class, we are going to move into the forced oscillation. That is, one more parameter is going to be added. So that we'll write down the differential equation. We'll solve those differential equation, and there again we'll see some of the very interesting example. So to keep your excitement again, you must have heard that in the court of the Akbar, a great musician Tansen was there, and when he used to play his musical instrument, the glass ceiling used to break. So how it was used, breaking. So all those things, some of those type of the example, maybe you will see over there, right? So next class we are going to start with the forced oscillation. For the time being, thank you very much. Watch all the video, and of course I will recommend that you must subscribe all the video, so the moment I'm going to upload the video, the notification will come to you. Thank you very much.